Hello everyone, this is the second paper in this series. Last time we read Word to Vec, where the whole point was turning words into numbers. And this time we are going to be reading Attention is All You Need from 2017. It introduces the concept of a transformer, and if you've heard of GPT or BERT, this is the paper underneath all of that. So the authors of this paper are Vaswani, Naum Shazeer, Nikki Parmar, Jakob Uszkoreit, Leon Jones, Aiden Gomez, Vukash Kaiser, and Ilya Polosukhin. Sorry if I mispronounced any names. First, let's go ahead and read the abstract. The dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. The best performing models also connect the encoder and decoder through an attention mechanism. We propose a new simple network architecture, the transformer, based solely on attention mechanisms dispensing with recurrence and convolutions entirely. Experiments on 2 machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. Our model achieves 28.4 blue on the WMT 2014 English to German translation task, improving over the existing best results, including on Our model achieves 28.4 blue on the WMT 2014 English to German translation task, improving over the existing best results, including ensembles by over 2 blue. On the WMT 2014 English to French translation task, our model establishes a new single model state-of-the-art blue score of 41.8 after training for 3.5 days on 8 GPUs, a small fraction of the training cost the best models from the literature. We show that the transformer generalizes well to other tasks by applying it successfully to English constituency parsing, both with large and limited training data. So let's go through what's actually being said in the abstract. The existing best models for tasks like translation use recurrent and convolutional neural networks, plus an attention mechanism bolted onto that. The move here is to throw away the recurrent and convolutional part entirely and build a model out of attention alone. That is entirely what they're pitching right here, and this model is called the transformer. Let's focus on this, more parallelizable. And 28.4 blue to 41.8. They back up this claim with 2 things. One, it trains faster because it can be parallelized, meaning more of the computation can happen at the same time instead of waiting on the previous steps. And 2, the actual translation quality, which is measured by this thing called the blue score, it beats the previous best results. Here, blue is a score for comparing machine-generated text to human reference translation, and is generally a scale from 0 to 100, and the higher, the better. So we have to treat it as a scoreboard number for now. Let's go on to the introduction. Recurrent neural networks, long short-term memory, and gated recurrent neural networks in particular have been firmly established as state-of-the-art approaches in sequence modeling and transduction problems, such as language modeling and machine translation. Numerous efforts have since continued to push the boundaries of recurrent language models and encoder-decoder architecture. So they start off by saying that recurrent neural networks and specific kinds of them like LSTM and gated recurrent networks have been the standard approach for tasks like language modeling and translation. Recurrent models typically factor computation along the simple positions of the input and output sequences. Aligning the positions to steps in computation time, they generate a sequence of hidden states, ht as a function of the previous hidden state, ht-1, and the input for position t. This inherently sequential nature precludes parallelization with training examples, which become critical at longer sequence length, as memory constraints limit batching across examples. Recent work has achieved significant improvements in computational efficiency through factorization tricks and conditional computation, while also improving model performance in case of the latter. The fundamental constraint of sequential computation, however, remains. This paragraph explains the actual problem. A recurrent model processes a sequence one step at a time, and each step's hidden state depends on the previous state. So to compute step 4, you need step 3 done first, which needs step 2 done first, and then so on. So you cannot skip ahead because it is entirely sequential. And the paper says this becomes a really important problem on long sequences because you cannot parallelize with one training example. Attention mechanisms have become an integral part of compelling sequence modeling and transduction models in various tasks, allowing models of dependencies without regard to their distance, the input or output sequences. In all but a few cases, however, such attention mechanisms are used in conjunction with a recurrent network. And here is the setup of their idea. Attention on its own isn't a new concept. It was already being used in translation models, but it's always paired with a recurrent network doing most of the heavy lifting. Here, attention was not the main model itself, and the question that they are posing here is, what if attention did the entire job by itself with no recurrence attached to it at all? In this work, we propose the transformer, a model architecture eschewing recurrence and instead relying entirely on attention mechanism to draw global dependencies between input and output. The transformer allows for the significantly more parallelization and can reach a new state of the art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. So this is the proposal that this paper is making, a model called the transformer that uses attention to connect every single part of the input to every part of the output with nothing recurrent in it at all. The goal of reducing sequential computation also forms the foundation of the extended neural GPU, ByteNet, and conv-S2S, all of which use convolutional neural networks as basic building blocks, computing hidden representations in parallel for all input and output positions. In these models, the number of operations required to relate signals from two arbitrary input or output positions grow in the distance between positions, linearly for conv-S2S and logarithmically for ByteNet. This makes it more difficult to learn dependencies between the distant positions. In the transformer, this is reduced to a constant number of operations, albeit at the cost of reduced effective resolution due to averaging attention-weighted positions, an effect we counteract with multi-head attention as described in section 3.2. This is comparing to a completely different family of models built on convolutions instead of recurrence. The issue that they point out in these models is the cost of connecting two positions in a sequence grows the further apart that the positions are. For one of them, it grows in a straight line with distance, and for the other, it grows more slowly, logarithmically, but it still grows. In the transformer, they say this becomes a constant number of operations no matter how far apart these two positions are. Self-attention, sometimes called as infra-attention, is an attention mechanism relating different positions of a single sequence in order to compute a representation of the sequence. Self-attention has been used successfully in a variety of tasks including reading comprehension, abstractive summarization, textual entailment, and learning task-independent sentence representation. So, self-attention, also called intra-attention, means relating different positions within a single sequence to build a representation of that sequence. So it's not the attention between two different sequences. It's a sentence paying attention to itself and to its own words. End-to-end memory networks are based on a recurrent attention mechanism instead of a sequence-aligned recurrence and have been shown to perform well on simple language question answering and language modeling tasks. To the best of our knowledge, however, the transformer is the first transduction model relying entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolutions. In the following sections, we will describe the transformer, motivate self-attention, and discuss its advantages over models. This is them stating the actual contribution. So to their knowledge at this point in time, this was the first model that kind of computes everything using self-attention by itself with no recurrent or convolutional layers at all in the inner workings. Model architecture. Most competitive neural sequence transduction models have an encoder-decoder structure. Here, the encoder maps an input sequence of symbol representations x1 to xn to a sequence of continuous representations z is equal to z1 to zn. Given z, the decoder then generates an output sequence y1 to ym of symbols one element at a time. At each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next. The transformer follows this overall architecture using stacked self-attention and pointwise, fully connected layers for both the encoder and decoder, shown in the left and right halves of this figure. Before all the transformer-specific stuff, this is just describing the general shape that the translation model already has. You feed in a sequence, the encoder turns it into some internal representation, and the decoder uses that representation to generate the output sequence one piece at a time. Autoregressive just means that when generating the next piece of output, the model also looks at the output that it has already generated so far, not just only the input. So let's just look at this diagram here. The left half is the encoder and the right half is the decoder, and everything flows upward from the bottom to the top. So starting from the bottom, inputs is just the sentence that you're feeding in as words or word pieces. Input embedding turns each of these into a vector or just a list of numbers, and it's the same idea as the word vectors from the word2vec video. Then this positional encoding basically marks each word's position in the sentence. Then it goes to multi-head attention, which is the actual self-attention step. Then add and norm, which I'll get to later, and a feed forward step, then another add and norm. This whole chunk, attention plus feed forward, plus the norm steps around them, that's one layer, and they stack n of these on top of each other, hence the times n on the left. Encoder and decoder stacks. Encoder. The encoder is composed of a stack of n is equal to 6 identical layers. Each layer has 2 sublayers. The first is a multi-head self-attention mechanism, and the second is a simple position-wise, fully connected feed-forward network. We employ a residual connection around each of the 2 sublayers followed by layer normalization. That is, the output of each sublayer is layer norm x plus sublayer of x, where sublayer of x is the function implemented by the sublayer itself. To facilitate these residual connections, all sublayers in the model as well as the embedding layers produce outputs of dimensions d model is equal to 512. So 6 identical layers stacked, that is what the value of n here is. Each layer has 2 parts, the multi-head attention and the feed-forward network. And here is what add and norm basically means. It's not a separate idea from the attention or feed-forward step. It's a wrapper around each of them. The formula here, layer norm of x plus sublayer of x, basically takes the input to this sublayer, runs it through the sublayer to get some output, then adds the original input back onto that output, and then normalizes the result. The add original input back is called a residual connection. It's a common trick that helps deep networks train, so you don't lose the original signal even after passing that through a transformation. Decoder. The decoder is also composed of a stack of n is equal to 6 identical layers, in addition to the 2 sublayers in each encoder layer. The decoder inserts a third sublayer which performs multi-head attention over the outputs of the encoder stack. Similar to the encoder, we employed residual connections around each of the sublayers followed by layer normalization. We also modify the self-attention sublayer in the decoder stack to prevent positions from attending to subsequent positions. This masking, combined with the fact that the output embeddings are offset by one position, ensures that the predictions for position I can depend only on the known outputs at positions less than I. Here they describe the decoder side, which also has 6 layers, but each layer has 3 parts instead of 2. First, there is the masked layer of that self-attention. Masked meaning it's only allowed to look at earlier positions in the output, not the later ones. They do this because at generation time, you haven't produced the later words yet. Second part is a multi-head attention step where this layer reaches over and attends the encoder's output, and that's how the decoder gets information about the input sentence. The third part is the same kind of feed-forward step as the encoder, and the same add and norm wrapping happens around each of these 3. Now, this arrow is the only connection between these 2 halves. Everything else, the encoder stack and most of the decoder stack, only talks to itself. It's specifically this one attention layer in the decoder that reaches across and looks at what the encoder is actually producing. Now, at the very top, after the decoder stack, there is a linear layer and a softmax, which turns the decoder's output into probabilities over the actual entire vocabulary. So basically, what's the most likely next word? This part is fairly standard and similar to what we saw in the word2vec video and the softmax discussion during it, and it's just applied here at the end of this much bigger model. Now, moving on to section 3.2, which is attention. An attention function can be described as mapping a query and a set of key value pairs to an output where the query keys, values, and outputs are all vectors. The output is computed as a weighted sum of the values where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. So before any formula, let's just understand this in simple English, because the entire rest of this section is just operations on these 3 things. Now, think of it like a lookup. The query is what are you searching for? Every item in your set has a key, which is like a label describing what that item is about, and the value is the actual content you would retrieve if the key matches. The output is a weighted blend of the values where the weight for each one depends on how well the key matches the query. So instead of one single lookup like a dictionary, it's a soft lookup where every item contributes a little bit, weighted by how relevant it is. Scaled dot product attention. We call our particular attention scaled dot product attention. The input consists of queries and keys of dimensions dk and of values of dimensions dv. We compute the dot products of the queries with all keys divided by whole root dk and apply a softmax function to obtain the weights of the values. In practice, we compute the attention functions on a set of queries simultaneously packed together into a matrix Q. The keys and values are also packed together into matrices K and V. We compute the matrix of the outputs as this. Alright, so first let's walk through this diagram, bottom to top, since that's the order that things actually happen in. Q, K, and V come in at the bottom. First, matma, which is matrix multiplication, multiplies the queries against the keys, and this is how well does this query match each key. It's that step. Now this produces a raw compatibility score for every single key query pair. Then scale divides those scores by the square root of dk, which is the dimension of the key vectors. Now there is an optional mask which only gets used in the decoder to block certain connections. Now the softmax turns the scores into proper weights that add up to 1. It's the same softmax idea as word2vec. Then the final matrix multiplication multiplies those weights against the values, giving you the actual weighted blend of the values, which is the final output. So this equation here is the entire diagram kind of condensed into this one line. Q times K transpose is the matrix multiplication of queries against the keys, giving you all those compatibility scores at once for an entire batch. And now dividing this by the root of dk, that is the scaling step. Softmax turns this into weights, and then you multiply it by v and you get the output. This one equation just explains this entire diagram. The two most commonly used attention functions are additive attention and dot product attention. Dot product attention is identical to our algorithm except for the scaling factor of 1 by root dk. Additive attention computes the compatibility function using a feed-forward network with a single hidden layer. While the two are similar in theoretical complexity, dot product attention is much faster and more space efficient in practice, since it can be implemented using highly optimized matrix multiplication code. So here they're explaining another older style called additive attention, which computes the compatibility score using a small feed-forward network instead of a dot product. They're saying that dot product attention is basically the same as theirs minus the scaling, and they pick dot product specifically because it can be computed using fast, optimized matrix multiplication code. While for small values of dk, the two mechanisms performing similarly, additive attention outperforms dot product attention without scaling for larger values of dk. We suspect that for large values of dk, the dot products grow large in magnitude, pushing the softmax function into regions where it has extremely small gradients. To counteract this effect, we scale the dot products by 1 by root dk. So here, the larger the value of dk, larger in magnitude the dot product grows, and the softmax kind of gets too confident and the gradients vanish. So to fix that, we are scaling the dot product by 1 by root dk. So just to summarize this again, if the key dimension is large, then the dot products between the query and the key tend to come out with an extremely large magnitude just from how the dot product works with more dimensions. So when you feed it large numbers into a softmax, it becomes really extremely confident and almost a hard yes or no rather than a smooth weighting. And this flattens out the gradient and makes it really, really small. So meaning the model has a hard time learning from it now. So dividing this by the square root of dk keeps those numbers in a more reasonable range so that the softmax stays smooth and the gradients still flow properly. Multi-head attention. Instead of performing a single attention functions with d-model dimensional keys, values, and queries, we found it beneficial to linearly project the queries, keys, and values h times with the different learned linear projections to dk, dk, and dv dimensions. On each of these projected versions of queries, keys, and values, we then perform the attention function in parallel, leading dv dimensional output values. These are concatenated and once again projected, resulting in the final values as depicted in figure 2. Multi-head attention allows this model to jointly attend the information from different representation subspaces at different positions. With a single attention head, averaging inhibits this. So here is the upgrade. Instead of doing the attention calculation once on the full-size vectors, they're splitting it up into smaller parts. First, they take the query's keys and values and run each one through a separate learned linear transformation, and they do this h different times. Here. Then you end up with h smaller versions, and each of these have different learned weights. So now you end up with h smaller versions of q, k, and v instead of just one big version. Then you run the scale dot product attention from before separately on each of these h smaller versions in parallel. So here it's basically saying they are doing multiple scale dot product attention blocks stacked one behind each other. In this work, we employ h is equal to 8 parallel attention layers or heads. For each of these, we use dk is equal to dv is equal to d model by h is equal to 64. Due to the reduced dimensions of each head, the total computational cost is similar to that of a single head attention with full dimensionality. These are the actual numbers for their model. It has 8 heads. Each head works with vector sizes of 64 because 512 divided by 8 is equal to 64. So nothing extra is being added in terms of total size, because the original 512 dimensional vectors is just being split into 8 chunks of 64, and they're being processed separately and then glued back together at the end. And it's glued back during this concatenation step, followed by one more linear layer. So going back to this sentence, multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions. This is the actual reason for doing this in this way instead of just one big attentional calculation. With only one head, you get one single weighting per position, and that one weighting has to average together everything that might be relevant, which can kind of wash out all the distinct kinds of relationships. With 8 separate heads, each one can specialize in different things, and so each head learns its own separate projection. Applications of attention in our model. The transformer uses multi-head attention in 3 different ways. In encoder-decoder attention layers, the queries come from the previous decoder layer and the memory keys, and the values come from the output of the encoder. Memory keys, and the value comes from output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanisms in sequence-to-sequence models. Alright. So in this specific attention layer, the queries come from the decoder. The keys and values come from the encoder's output. So the decoder is reaching over and asking the encoder, given what I am currently generating, what part of the input sequence is relevant to me. And every position in the decoder gets to look at every single position in the encoder's output here. Now, the encoder contains self-attention layers. In a self-attention layer, all of the keys, values, and queries come from the same place. In this case, the outputs of the previous layers in the encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder. Now, this is self-attention. Inside the encoders, queries, keys, and values all come from the same exact source, which is the previous layer's output. So the sentence is comparing all of its own words against each other and deciding which other words in the same sentence are relevant to each word. Similarly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up to and including that position. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. Prevent leftward information. We implement this scaled inside of scale dot product attention by masking out, setting to negative infinity, all values in the input of the softmax which correspond to illegal connections. This is basically describing the masking that we described earlier in the diagram. So in the decoder's self-attention, a position is only allowed to attend to itself and earlier position, never the ones that come afterwards. This is because, let's say you're generating words, you're generating word 3. Now, word 4 and 5, they don't exist yet because we haven't produced them yet. The way they implement this is before the softmax step, they set the score for any illegal connection, meaning any future position, to negative infinity. So when you run a softmax on negative infinity, it comes out to 0. So these future positions just get a weight of 0 automatically without needing to have a separate filtering step. Position-wise feed-forwarding networks. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network, which is applied to each position separately and identically. This consists of 2 linear transformations with an ReLU activation in between them. Now, equation 2 says f of n x is equal to max of 0 and xw1 plus b1 multiplied by w2 plus b2. This is the feed-forward box from the diagram. It's pretty simple compared to the attention math. It's 2 linear transformations with the ReLU activation squeezed in between them. ReLU just means that anything negative gets clamped to 0 and everything positive remains unchanged. Now the important detail is that this gets applied to each position within one layer but has different weights from layer to layer. But the important detail here is that this gets applied to each position in the sequence completely separately, using the same weights for every position within one layer, but has different weights from layers to layer. So unlike attention, which kind of mixes information across positions, this step doesn't let positions talk to each other at all. It's working on each of these completely independently. Now, while the linear transformations are the same across different positions, they use different parameters from layer to layer. Another way of describing this is as 2 convolutions with kernel size 1. The dimensionality of input and outputs is d mod is equal to 512, and the inner layer has dimensionality dff is 2048. Now the numbers here, input and output, are the standard 512 dimensionality size, but inside this feed forward block, it briefly expands to 2048 dimensions before coming back down to 512. So there's like a wider hidden layer somewhere in the middle. Embeddings and softmax. Similarly to other sequence transduction models, we use learning embeddings to convert the input tokens and output tokens to vectors of dimension d model. We also use the usual learned linear transformation and softmax function to convert the decoder output to predict next token probabilities. In our model, we share the same weight matrix between the 2 embedding layers and the pre-softmax linear transformation. In the embedding layers, we multiply those weights by root d model. Okay. This is just confirming what we learned before. Learned embeddings turned input and output tokens into 512 dimensional vectors. And a final linear layer plus a softmax turns the decoder's output back into next token probabilities. So they share the same weight matrix between the input, the output embedding, and the final pre-softmax layer, instead of learning 3 separate ones. Positional encoding. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence. To this end, we add positional encodings to the input embeddings at the bottom of the encoder and the decoder stacks. The positional encodings have the same dimension D model as the embeddings so that the two can be summed. There are many choices of positional encodings, learned and fixed. In this work, we use sine and cosine functions of different frequencies. Alright. Self-attention by itself treats the input like a bag of words. It doesn't have a sense of order. Now, a recurrent network naturally knows that position 1 comes before position 2 because it processes them one at a time and it does it in order. The transformer doesn't process things in order at all. Every position is held in parallel to each other. So if you don't do something extra, the model cannot tell between the order of this information. Now, this is the whole reason that this section exists. They have a separate signal, the positional encoding, which is directly on the embedding so that positions get baked in from the very start. As you can see from our diagram here, positional encoding right after the input embedding. Alright. Now let's look at these different equations. PE pos 2i is equal to sine pos by 10,000 raised to 2i divided by t model. And here, same thing but with 2i plus 1 and cos. Now the actual mechanism is the sine and cosine waves. Each dimension of the positional encoding follows a wave, and different dimensions use different frequencies. Some waves complete a cycle quickly and some do it very slowly. So for any given position, you get a unique combination of values across all of these different frequency waves, kind of like a unique identification for that position, built from this sine and this cosine. Here, pos is the position and I is the dimension. That is, each dimension of the positional encoding corresponds to a sinusoid. The waves form a geometric progression from 2 pi to 10,000 times 2 pi. We choose this function because we hypothesized it would allow the model to easily learn to attend by relative positions. Since for any fixed offset k, PE pos plus k can be represented as a linear function of PE pos. We also experimented with using learned positional embeddings instead and found that the two versions produce nearly identical results. We chose the sinusoidal version because it may allow the model to extrapolate to sequence lengths longer than the ones we encountered during training. Okay, so this is the reason they've given for this specific choice. They wanted the model to be able to learn relative position, meaning how far apart are the two words. With sine and cosine, there is a mathematical property where shifting by a fixed distance can be expressed as a simple linear transformation of the of the original encoding. And one more useful note, they also tried learning the positional encodings differently, the same way you would do on a word embedding, and it gave nearly the same results, but they went with the sine and cosine version anyways, betting that it might actually generalize better to sequences longer than what they've seen during training, since the wave pattern keeps making sense indefinitely, whereas a learned encoding for, say, position 500 only exists if you actually trained on sequences which are that long. Now, why self-attention? In this section, we compare various aspects of self-attention layers to the recurrent and convolutional layers commonly used for mapping one variable length sequence of symbol representations, x1 to xn, to another sequence of equal length, z1 to zn, with xi, zi belonging to Rd, such as hidden layers in a typical sequence transaction encoder or decoder. Motivating our use of self-attention, we consider three desiderata. One is the total computational complexity per layer. Another is the amount of computation that can be parallelized as measured by the minimum number of sequential operations required. The third is the path length between long-range dependencies in the network. Learning long-range dependencies is a key challenge in many sequence transduction tasks. One key factor affecting the ability to learn such dependencies is the length of the paths forward and backward signals have to traverse in the network. The shorter these paths between any combination of positions in the input and output sequences, the easier it is to learn long-range dependencies. Hence, we also compare the maximum path length between any two input and output positions in networks composed of different layer types. Alright, so here is our checklist. First is total cost per layer. Second is, can it be parallelized? And the third is this path length. Basically saying how far does a signal have to travel between these two positions. Now this whole section is comparing self-attention against recurrent and convolutional layers on three specific measuring scales. One is this one, parallelizable, and then length. Now, how expensive one layer is to compute, how much of that layer can happen simultaneously, and how many steps does this information have to travel to connect two positions that are far apart. This third one connects back to something that we said all the way in the background section, that shorter paths make long-range dependencies easier to learn. As noted in Table 1, a self-attention layer connects all positions with a constant number of sequentially executed operations, whereas a recurrent layer requires O of n sequential operations. In terms of computational complexity, self-attention layers are faster than recurrent layers when the sequence length n is smaller than the representation dimensionality d, which is most of the case with sentence representations used by state-of-the-art models in machine translation, such as word piece and byte pair representations. To improve computational performance for tasks involving very long sequences, self-attention could be restricted to considering only a neighborhood of size r in the input sequence centered around the respective output position. This would increase the maximum path length to O n by r. We plan to investigate this approach further in future work. So let's take a look at Table 1 here. So let's go through this table slowly because it kind of summarizes the entire trade-off that we talked about. Self-attention's cost per layer depends on n squared times d, where n is the sequence length and d is the vector dimension. But its sequence operations and its maximum path lengths are constant. So it doesn't get more sequential as the sentence grows, and its maximum path length between any two positions also is constant. Now, recurrent layers have a cheaper looking cost per layer because it's just n times d squared, but their sequential operations scale directly with n, and so does the path length. And this is because information has to pass through every single step in between. Convolutional layers seem to kind of lay somewhere in between, and this fourth row, self-attention, it only looks at the neighborhood of size r instead of the entire sequence. So it trades some of that constant path length back for cheaper computation on very large sequences. Now, a single convolutional layer with kernel width k less than n does not connect all pairs of input and output positions. Doing so requires a stack of O n by k convolutional layers in the case of contiguous kernels, or O log kn, in the case of dilated convolutions, increasing the length of the longest path between any two positions in the network. Convolutional layers are generally more expensive than recurrent layers by a factor of k. Separable however, decrease the complexity considerably to O of k times n times d plus n times d squared. Even with k is equal to n, however, the complexity of a separable convolution is equal to the combination of a self-attention layer and a pointwise feed-forward layer, the approach we take in our model. A side benefit, self-attention could yield more interpretable models. We inspect attention distributions from our models and present and discuss examples in the appendix. Not only do individual attention heads clearly learn to perform better tasks, many appear to exhibit behavior related to the syntactic and semantic structure of these sentences. Okay, so let's summarize these last 3 paragraphs. Here it basically says that self-attention is only cheaper when the sequence length n is smaller than the vector dimension. And they're saying that condition is usually true in practice for the sentence lengths and dimension sizes used in translation. So the constant path length benefit comes with the fact that n squared cost per layer, which is fine for normal sentence lengths, but would get really expensive for very long sequences, which is exactly what the restricted self-attention row in the table is meant to address. And one more claimed side benefit is that the attention weights themselves might be easier to inspect and interpret than the internals of a recurrent network, because you can literally look at which words a given head is paying attention to at any point of time. Okay, so training data and batching. We trained on the standard WMT 2014 English-German dataset consisting of about 4.5 million sentence pairs. Sentences were encoded using byte pair encoding, which has a shared source target vocabulary of around 37,000 tokens. For English-French, we use a significantly larger WMT 2014 English-French dataset consisting of 36 million sentences and split tokens into a 32,000 word piece vocabulary. Sentence pairs were batched together by approximate sequence length. Each training batch contained a set of sentence pairs containing approximately 25,000 source tokens and 25,000 target tokens. This is just the practical setup. It has 2 translation data sets, English to German and English to French, and the French one was much bigger. These sentences got broken into subword pieces rather than whole words, and it was done so using byte pair encoding or word piece encoding. And that's the detail about the vocabulary size management. And they group these sentences of similar length into the same batch just for practical purposes. Now, hardware and schedule. We trained our model on one machine with 8 NVIDIA P100 GPUs. For our base models using the hyperparameters described throughout the paper, each training step took about 0.4 seconds. We trained the base model for a total of 100,000 steps or 12 hours. For our big models described on the bottom line, step time was 1 second. The big models were trained for 300,000 steps or 3.5 days. So this is where that 12 hours claim came from the introduction. There's also a bigger version of the model, and the differences are mentioned in this table 3. Now, optimizer. We use the Adam optimizer with beta 1 is equal to 0.9, beta 2 0.98, and epsilon 10 raised to minus 9. We varied the learning rate over the course of training according to the formula L rate is equal to d raised to minus 0.5 times minimum of step num raised to minus 0.5 or step num times warm-up steps raised to minus 1.5. Now the learning rate, which is basically how big a step the model takes while learning, is not constant here. It's varied. It follows a specific shape over the course of the training. Now for the first chunk of the training, called the warm-up steps, it increases in a straight line. After that, it decreases following an inverse of the square root of that number, and it just gradually keeps shrinking. Now the idea is, even though they don't spell out the reasoning explicitly here, is generally that you want a small, careful step right at the very start while the model's weights are still random and unstable, and then you can briefly speed up and then taper off as training progresses, so it can settle into a good solution rather than overshoot. And they used 4,000 warm-up steps specifically. Okay. Regularization. We employed 3 types of regularization during training. Residual dropout. We apply dropout to the output of each sublayer before it is added to the sublayer input and normalized. In addition, we apply dropout to the sums of the embeddings and the positional encodings in both the encoder and decoder tasks. For the base model, we use a rate of p drop is equal to 0.1. And label smoothing. During training, we employed label smoothing of values. Epsilon ls is equal to 0.1. This hurts perplexity as the model learns to become more unsure but improves accuracy and blue score. Now, it's mentioned 2 regularization tips, meaning these are techniques to prevent the model from overfitting to the training data. Now, dropout, which is applied at a rate of 0.1 for the base model, randomly turns off some connection during training, applied to the output of each sublayer and also to the embeddings and positional encodings. And label smoothing, set to 0.1, deliberately makes the model less than fully confident about the correct answer during training. So they note that this makes the model's stated confidence, or also called perplexity, worse, but it improves the actual accuracy and the blue score. So it's here. So it's a case of the number going in the wrong direction on purpose because the real world result actually improves. So let's take a look at the results. On the WMT 2014 English to German translation task, the big transformer model outperforms the best previously reported models by more than 2.0 blue, establishing a new state-of-the-art blue score of 28.4. The configuration of this model is listed in the bottom line of Table 3. Training took 3.5 days on the 8 P100 GPUs. Even our base model surpasses all previously published models and ensembles, at a fraction of the training cost at any of the competitive models. On the WMT 2014 English to French translation task, our big model achieves a blue score of 41.0, outperforming all of the previously published single models at less than 1/4 of the training cost of the previous state-of-the-art model. The transformer model, trained for English to French, used the dropout rate p drop as 0.1 instead of 0.3. For the base models, we used a single model obtaining by average of the last 5 checkpoints, which were written at 10-minute intervals. For the big models, we averaged the last 20 checkpoints. We used beam search with a beam size of 4 and length penalty alpha is 0.6. These hyperparameters were chosen after experimentation on the development set. We set the maximum output length during inference to input length plus 50, but terminate early when possible. Table 2 summarizes our results and compares our translation quickly and training cost to other model architectures from the literature. We estimate the number of floating point operations used to train a model by multiplying the training time, the number of GPUs used, and an estimate of the sustained single precision floating point capacity of each GPU. So let's take a look at Table 2 and read the scoreboard. Now, here is a list of the previous models, including some that are ensembles, meaning multiple models combined together for a boost. The transformer big model gets 28.4 blue on English to German, beating all of them, even the ensembles, and it gets 41.8 on the English to French, which is also a new best for a single model. And now looking at the training cost column, it's measured in floating point operations, and the transformer's cost is dramatically smaller than any other model on the list, especially the ensembles. So they didn't just get a better score, but they also got a better score with notably less computation required. A quick mention of how they actually generate the output. Here, beam search means instead of greedily picking the single most likely next word at each step, you keep a small set of the most promising partial sentences. So here, a beam of 4 and expand all of them and keep the best ones as you go. This generally gives a better final result than always taking the single best next word at every step. Now let's take a look at the model variations. To evaluate the importance of different components of the transformer, we varied our base models in different ways, measuring the change in performance on English to German translation on the development set. New test 2013. We used beam search as described in the previous section, but no checkpoint averaging. We present these in table 3. So let's take a look at table 3. This is them taking the base model and changing one part at a time to see which parts actually matter. And every single row is a variation from that base setup, and the PPL and blue, these columns on the right, show what actually happened to the performance. So let's take a look at row A. Here we are testing the multi-head idea directly. So one head alone gives the worst possible score, confirming that splitting into multiple heads genuinely helps, not just theoretically. But it's not that more heads is always better, because the score goes up for 16 heads, but once it reaches 32, it dips slightly. So there is a certain sweet spot, and the chosen value of 8 is right around there. Now looking at row B, it shrinks the dimensionality of the key, and that definitely hurt the results. Their own interpretation is interesting because they're saying that this hints that figuring out how well a query matches a key isn't a trivial problem, and that a fancier compatibility function than the plain dot product might do even better. They're not claiming dot product is definitely optimal, but it's good enough and it's fast. Now C and D. These are a little bit less surprising because bigger models, meaning more layers or wider vectors, generally score better, and dropout meaningfully helps avoid overfitting. So you can see in row D that turning dropout off entirely, the 0.0 rows, gives even worse scores than keeping it on. Now taking a look at E. E is the one that we already have covered. We're swapping in learned positional encodings instead of the sine and cosine version, and it gives almost the same score. 25.7 versus the model's 25.8. So this kind of confirms what they said earlier, that the specific choice of positional encoding scheme doesn't matter that much for performance on sequences of this length, because the sinusoidal choice was more about a bet on was better for longer sequences than about accuracy. Now here, big. This bottom row is the bigger model with double the layer width, quadrupled feed-forward dimensions, more heads, more dropout, and trained for 3 times as many steps, like 300k instead of 100k. Now here it landed at 26.4 blue on the developmental set, ahead of everything above it. Now let's take a look at English constituency parsing. To evaluate if the transformer can generalize to other tasks, we perform experiments on English constituency parsing. This task presents specific challenges. The output is subject to strong structural constraints and is significantly longer than the input. Furthermore, RNN sequence-to-sequence models have not been able to attain state-of-the-art results in small data regimes. We trained a 4-layer transformer with D models is equal to 1024 on the Wall Street Journal WSJ portion of the Penn Tree Bank, about 40k training sentences. We also trained it in a semi-supervised setting using the large high-confidence and Berkeley parser corpora from with approximately 17 million sentences. We used a vocabulary of 16k tokens for the WSJ, only setting and a vocabulary of 32k tokens for the semi-supervised setting. We performed only a small number of experiments to select the dropout. Both attention and residual learning rates and beam size on section 22 developmental set All other parameters remain unchanged from the English to German based translation model. During inference, we increase the maximum output length to input plus 300. We used a beam size of 21 and alpha 0.3 for both WSJ only and the semi-supervised setting. Our results in Table 4 show that despite the lack of task-specific tuning, our model performs surprisingly well, yielding better results than all previously reported models, with the exception of the recurrent neural network grammar. In contrast to iron and sequence-to-sequence models, the transformer outperforms the Berkeley parser, even when training on only WSJ training set for 40K sentences. So this is a different task entirely here. Parsing means to figure out a sentence grammatical structure, which clauses and phrases nest inside. So basically, they're testing whether the transformer is useful beyond just translation. Because here, the output here has strict structural rules and it tends to be longer than the input. And this is a much different shape of challenge than just plain translation. Now they trained a small 4-layer version both on a smaller label dataset alone and combined with a much larger semi-supervised one. Now let's look at this table 4. This shows the result, and you can see the transformer does surprisingly well here too. It beats most of the existing parsers listed, both with and without the extra semi-supervised data, even though they didn't tune it specifically for this task. It does fall short of recurrent neural network grammars, which was built for this exact purpose, but the takeaway isn't that a transformer wins at everything. It's that this is a general purpose architecture that holds up well even outside of the tasks that it was designated for. Now the conclusion. In this work, we presented the transformer, the first sequence transduction model based entirely on attention, replacing the recurrent layers most commonly used in encoder-decoder architectures with multi-head self-attention. For translation tasks, the transformer can be trained significantly faster than architectures based on recurrent or convolutional layers. On both WMT 2014 English to German and WMT 2014 English to French translation tasks, we achieve a new state-of-the-art. In the former task, our best model outperforms even all previously reported ensembles. We are excited about the future of attention-based models and plan to apply them to other tasks. We plan to extend the transformer to problems involving input and output modalities other than text and investigate local restricted attention mechanisms to efficiently handle large inputs and outputs, such as images, audio, and video. Making generation less sequential is another research goal of our own. So let's retrace this for ourselves as well. And let's take a look at this diagram again. So now this whole thing started from one specific complaint that recurrent models force you to compute one step at a time, which limits how much you can parallelize, and it makes long sequences extremely slow to train on. So the fix was remove recurrences entirely and build the model purely out of attention. So now self-attention inside the encoder, it lets every single word look at every other word in the same sentence directly with a constant number of steps regardless of the distance. And now multi-head attention, it splits that process into several smaller parallel versions so that the model can track more than one kind of relationship at once. So since attention alone has no sense of order, they added this positional encoding built from sine and cosine waves directly onto the input. And this decoder reuses the same attention mechanism 3 different ways. Masked self-attention over its own previous outputs and the attention over the encoder's output to read the source sentence. And then it has a feed-forward network applied to each position. And so the result of all of that was an improvement in training cost, and it even held up on completely different tasks, which was parsing, that the model wasn't even specifically designed for. So they closed by saying that they wanted this approach to be pushed towards other types of data entirely, including images, audio, video, and towards making the general process less sequential. Now, Having watched this play out since 2017, it's a pretty understated way of describing what has actually happened in the field after that. All right. So, thank you so much. This is the end of this paper.